So it's a pleasure to introduce Aswani. She got her PhD from Johannes Gutenberg University in Mainz, working with Professor Wolfgang Trimmel, followed by a postdoc at the Lab of Photonics and Interfaces at EPFL in Switzerland, where she received an award, and I think I'm going to murder the name of the award. So maybe Aswani will tell you the correct name after this. It's some EPFL prestations, something. It says exceptional, and she received it in the year 2011. And she indeed is exceptional. We tried very hard to convince her to join the department, and we succeeded, which is great for the department. She joined us in the year 2015 and has been working, rather her group has been working on hybrid halide perovskite materials for various optoelectronic devices. She has been hailed as a rising star by ACS in the area of energy and fuels. So it's my pleasure to invite Aswani to give her talk.
Good afternoon, everyone, and thank you very much, Rita, for the nice introduction. And thanks also to the Institute Award, IRCC Award Committee for recognizing our work and for giving this award. And today I will be talking about hybrid halide perovskites. These are typical, the halide perovskites are very well known in the field of solar cells. But today what I will be speaking about is not about the application in solar cells, but in terms of other applications other than photovoltaics, like other optoelectronic devices like light emitting diodes and so on. So this is the outline of my talk, where I will give a brief introduction about these halide perovskites, and then the light emitting diodes, the work on the light emitting diodes that we have done, and the moisture to electricity conversion, and of course the conclusions. So the perovskite solar cells that we are working on is based on actually this methylammonium lead iodide, where we have methylammonium is the A cation in the perovskite structure, and the lead is actually the B cation in this perovskite structure, and the iodine or any other halide is the X anion that is in the 3D perovskite, that is the structure of it is shown over here. So typically this particular material has a very interesting properties for photovoltaic applications. So they are like this material can be crystallized at very low temperatures. If we compare it with silicon solar cells needs temperatures more than 1500 degrees centigrade for them to crystallize. Whereas this particular material, that is the methylammonium lead iodide, which is a hybrid organic inorganic material, can be crystallized at temperatures as low as 60 degrees centigrade temperature. So of course the cost of making the solar cells will be very less when the crystallization temperature is lower. Then the second important property is that this material has got a very high optical absorption coefficient, which means that if we are, if the optical absorption coefficient is higher, then we need actually a very thin layer of the material to absorb all the visible part of the spectrum. So if we compare it with the silicon solar cells roughly require 300 micrometer thick film to absorb the solar spectrum, whereas this particular methylammonium lead iodide requires only 300 nanometer thick film. So it's actually 3 orders of magnitude less thickness that we need for the absorption of the visible light from the solar spectrum. Then the other interesting parameters that it has is that it has got excellent charge carrier transport properties, like diffusion lengths are in the order of few micrometers, whereas the thickness that we need is only a few hundreds of nanometers we need, but the diffusion length that this material possesses is in micrometer range. And so because of all these excellent properties, the solar cell applications of these materials are the efficiency of the solar cells has quickly raised. The material has the first initial reports of the solar cells have started in 2011, and from 2011 to 2024 now the efficiency has raised from almost from 10% to 25.6% is the highest efficiency right now for these solar cells. If we compare it with the silicon solar cells, silicon in the lab scale is only 27 right now. And this material in 10 years or 12 years of time, this has achieved almost similar efficiencies as the silicon solar cells. So that's why this material is very interesting in terms of the application to solar cells. Yeah, this is actually the efficiency chart, where there is a National Renewable Energy Laboratory in the US, and this renewable energy laboratory certifies the efficiencies of all the lab scale devices. And the perovskite solar cells, you can see that there is actually a steep rise, these yellow dots with the red line that is connected. So this is the one that is corresponding to the silicon for the perovskite solar cells, and compared to any other technology, the rise in the efficiency is very steep. But of course, this material has got some, even though it has got so many advantages, it has got also so many other problems that are associated with it. One of it is actually, this material is lead based, which means that this is toxic. So even silicon solar cells has got the lead, that is the lead in the soldering of the silicon solar cells, but the lead that is present in the silicon solar cells is in the form of metallic lead. So metallic lead is not soluble in water and it's not toxic, but here the lead is present as lead 2+, which makes it water soluble and it is toxic. And the second thing is, this material can be crystallized at 60 degrees centigrade temperature, which means that any material that is easy to make is also easy to break. So that means that it is also unstable with all these conditions like temperature, humidity, UV radiation, and so on, so on. Especially in Mumbai conditions, which is hot and humid in most of the days, we see that methylammonium lead iodide methylammonium lead iodide gets converted into the lead iodide film within a few days, because the average relative humidity in Mumbai is around 76%. So within a week's time, you see that the film which is absorbing the visible light gets converted into an yellow colored film, which doesn't absorb much of the visible part of the spectrum. And the same is the case when we replace with the iodine with the bromine. It's slightly more stable, but it also degrades in the presence of the humidity. So that's the reason why the perovskite solar cells haven't been yet been commercialized, even though it has got much higher efficiencies and very good performance and the properties and so on, but still they are not actually commercialized yet. So what we thought is that, can we use these perovskite materials for some low maintenance devices? For example, something like a light emitting diodes or any other applications which doesn't need as high maintenance as the solar cells. So the first thing that we thought is, what happens if we replace the lead with other elements? So if we replace lead with other elements, we don't end up getting actually the 3-dimensional structure. For example, if we replace actually the lead 2+ with the antimony, which is a 3+ cation, so we end up getting a 2-dimensional perovskite. So these are only connected in 2 dimensions, but in the 3rd dimension these are not connected. There is a breaking of this thing in the crystal structure. So we end up getting a 2-dimensional perovskite. Or if we replace with the 4+ cations, then we end up getting actually a vacancy ordered double perovskite, which is here. You can see this is actually a double, the perovskite structure is double in terms of the unit cell, but now in every alternate cation is actually missing. So this is actually called as a vacancy ordered double perovskite. We can also form actually double perovskites, which means that we can replace the 2+ cation with 1+ cation and another one with a 3+ cation. So that we end up getting actually something like this, which is here we have replaced lead with one Ag+ ion and one bismuth 3+ ion. So this forms a double perovskite structure. So even though we can make actually these perovskite materials, the double perovskites and so on, but these are not really having very good band gaps. So the band gap is important because if we want to absorb the solar spectrum, then we need to have a band gap roughly of around 1.5 electron volts. But these double perovskites, most of the double perovskites have got actually the band gap which is of around 2.5 to 3 electron volts, which makes it which makes the material not really absorbing the visible part of the spectrum. It's only absorbing the UV part of the spectrum, but not the visible part. So we cannot really use these materials for the solar cell applications, or the 2-dimensional materials also we will not be able to use because there is no connectivity in the 3rd dimension. So the charge transport is hindered. Even the vacancy ordered double perovskites we will not be able to use because the charge transport is hindered in all the directions. So the best choice was to actually use these double perovskites. So one of the strategy that we thought was that to change the band gap, we can do actually the doping of this material with the other elements. So one of the things that we did was to dope the CS2Ag BiBr6 or CS2Ag InCl6 has a band gap of 3.3 eV. And CS2Ag BiBr6 has got an indirect band, it's an indirect band gap semiconductor, which has a band gap of around 2.5 eV. So we doped actually the CS2Ag InCl6 with that of bismuth to see if we can actually modulate its properties. So when we doped actually CS2Ag InCl6 we doped with different concentrations, and the structure still retains the double perovskite. This is the X-ray diffraction patterns. And from the X-ray diffraction patterns, we could see that the structure is retained with the double perovskite structure even after doping with 30%, alloying with 30% or 60% of the bismuth, and even with the pure bismuth also, we ended up getting the double perovskite structure. So when we measured when we incorporated the bismuth, there is a slight lattice expansion that is seen, and because bismuth is now occupying the indium sites, since it's bigger than the indium, bismuth is bigger than indium, so we have actually the lattice expansion that is taking place, which can be seen from the X-ray diffraction patterns. So when we measure the absorption spectrum of the pure CS2Ag ion Cl6, it has a band gap of around 3.3 eV, so it doesn't absorb anything in the visible part of the spectrum. And the CS2Ag BiCl6 has got a small absorption peak at around 380 nanometers. And but when we doped it with the bismuth, when we doped the CS2Ag ion Cl6 with the bismuth, we see that this peak at 370 nanometers is actually enhanced with the bismuth doping. So there is no significant shift in the absorption that is observed, only the intensity of the absorption has actually increased. So we calculated also the band gap. The band gap remained more or less similar for all these materials. And the interesting thing that came out from this one is that when we actually did the emission studies, the photoluminescence or the emission of the excited electron hole pairs, so that we saw that for the case of pure CS2Ag ion Cl6, we don't see much of the luminescence that is observed. And even in the case of CS2Ag BiCl6, the emission is roughly around 420 nanometers in the case of CS2Ag BiCl6. So typically when we measure the emission, we expect something like a sharp emission that is coming up from any kind of material. So this is for the case of CS2Ag BiCl6, where we see an emission that is not very broad. But when we do the same thing with the bismuth doped material, what we ended up getting is actually a broad emission. We could compare this. The red one is actually the emission that is coming up from the CS2Ag BiCl6, whereas this one is actually bismuth doped CS2Ag ion Cl6. So after doping with the bismuth, the emission, the FWHM of this peak is much more broader. So you can see the same thing is actually zoomed in over here between 400 to 700, and it's a very broad emission that is observed for the case of the after bismuth doping. So approximately 30% of the bismuth shows the emission that is covering the entire visible part of the spectrum, which is coming from 400 to 700 nanometers. So the entire visible, so because of which what we see is that when we make the LEDs out of, when we coat a UV LED with this material, what we ended up getting is actually a white light emission, because the emission is now covering up the entire visible part of the spectrum. So that's the reason why we see it as a white light. If we use actually pure bismuth, we end up seeing actually a blue emission because its emission is sharp, but when we are using 30% of the bismuth, we ended up getting emission which is corresponding to the emission from the pure white light. So this is actually the CIE diagram, which shows that the one that is at 30% bismuth is very close to the white light emission. So if the white light emission is there, then we'll have the point at 0.33, which means that we have red, green, and then the blue contribution coming up in 33%. So that will be at 33% and 33%, and this particular 30% bismuth has got a CIE coordinates of 0.36 and 0.35, which is very close to the white light emission, and it's also the CRI, which is the color rendering index, which means that in terms of in comparison with the sunlight, how does this light makes the visibility in terms of the color. So the color rendering index is also close to 91. So for the sunlight we take it as 100, and for this, if we are using this as our artificial light, then the color rendering index is almost 91 for this material. And the correlated color temperature is also something that is 4443. If it is roughly 2700, we say that we have a warm white light. But if it is close to 4000, we say that it's a neutral white light that is present. And if it is more than 5000, then we say that it's a cool white temperature, cool white color. So the color correlated temperature corresponds also to more neutral temperature that we have. But of course, one of the disadvantages is that the PL quantum yield, which means that how many photons are being absorbed and how many photons are being actually emitting. So that value is not very high, because if you consider actually 30% bismuth is the one which has actually the wide emission. So for the 30% bismuth, we only have the quantum yield of 3.9%, which is actually very small, which means that if we are taking up 100 photons, we are only converting 4 photons out of that into the emission, so which is very less. So can we actually increase the PL quantum yield? So for that we tried actually doing a heterovalent doping in the CS2Ag ion Cl6 by using strontium atoms. So when we did the heterovalent doping with strontium, Until 6% we see that the pattern more or less matches with the double perovskite, but after the 6.25% we see that there is some impurity that is starting to come. So the optimum dopant concentration that we can get is around 6.25% for the heterovalent doping. But now we don't see for this 6.25 doped strontium, we don't see a very broad emission, but only thing that we see is that compared to the undoped sample, we have a much higher intensity in the PL. Only the PL quantum yield has increased, but that means that the radiative recombination has actually increased, but the non-radiative recombination has reduced. So the 6.25% has given the PLQY of roughly 23.6%. So that means that we are taking 100 photons and converting around 24% of the 24 photons to the light in this strontium doped sample. So now we also say normally when we actually have two different perovskites, so we cannot mix those two perovskites because we always have actually anion exchange that is taking place. If you have a bromide and iodide perovskite, the anion exchange takes place and we end up getting an emission which is corresponding to the mixed halide perovskite. But we have actually strategically taken actually this 6.25% doped sample with another layered perovskite, another zero-dimensional perovskite, which is the DAO-SN2I6, and this has got a red emission, and we combined these two materials, which is having a blue emission and then the red emission, and this is more or less bluish green emission and then the red emission, and we ended up getting actually a white light emission. So the 6.25% doped sample in the CIE coordinates has got around 0.2, whereas for the DAO-SNI6 is around 0.5, and the white light emission that after combining these two materials we ended up getting is a white light emission which is right at the center, which corresponds to the 0.3. And the color rendering index of this particular material, of this combination of the two perovskites, is also around 94, and the good thing is that the luminance efficiency of the irradiation is also 229 lumens per watt. So which is actually very high in comparison to any of the other reported materials for this lead-free perovskites. So by combining these two perovskites, we have achieved that. So we also pumped it by using a UV LED, and you could see that as we are increasing the bias voltage, we could see the emission keeps increasing, which means that the radiative recombination is actually much higher when we are actually going to the higher voltages because of the higher amount of the light this thing. And the transmittance is one of the thing is that both the materials are completely transparent to the visible light. So they don't absorb anything in the visible part of the spectrum. So you can see that this is the combination of the two materials, 6.25% strontium and the DAO-SNI6, and there is no absorption coming up in the visible part of the region. But even though it doesn't absorb anything in the visible part of the spectrum, we end up getting actually a white light emission from this one. So that means that it's a visible light transparent material which emits a visible light, which emits complete visible light, which is a white light. And we could also see the stability of this material in terms of when we continuously run this material, then we end up getting actually the color coordinates or the color rendering index or the correlated color temperature doesn't change much when we keep running it for 2 hours roughly. So with this, I will actually quickly move on to the next application that I wanted to show, which is related to the moisture to electricity conversion, where I told in the beginning that when we have actually this perovskite, it converts methylammonium lead iodide, it converts to lead iodide in a span of 1 week. So the methylammonium iodide that is present is basically degrading in the presence of humidity, and we end up getting a lead iodide. So what we found out was that when we have excess methylammonium lead iodide, instead of having this 3-dimensional perovskite structure, we end up getting actually a 0-dimensional perovskite structure where all the PbI6 octahedra are not connected in any of the dimensions. So this particular material, when we keep when we put it under different humidity conditions, we end up getting actually this material converts itself to the 3-dimensional perovskite. So when we use this material, so since this material is not connected in any of the dimensions, it is insulating, and this material is connected in all the 3 dimensions. So this will be actually semiconducting. So that means there is a difference in the conductivity, and so we thought of using it for a humidity sensor. So our device is actually a pretty simple device where we have an FTO glass and then we coated it with this 0-dimensional perovskite, and then we saw that when we put them under humid conditions, there is an open circuit voltage that is generated. So the minimum in the current is now around 0.5 volts, which means that there is actually some power that is generated from these devices. So the voltage is around 0.5 volts, which is sustained for many hours, and the current is also sustained for roughly around 10,000 seconds. and we varied the humidity, and then we found out that at 65% humidity we ended up having this maximum amount of the voltage and the current that is generated. So this is at 65% RH, we have the maximum voltage, and the current density is also intermediate over there, and so we ended up getting actually the maximum power at around 65 to 70% RH. Yeah, so this is actually the power density which is maximum at around certain resistance that is actually offered. So we ended up getting a power from this device roughly around 400 milliwatt per meter square. So if we connect because the power is low, we can connect them in series or we can connect them in parallel, and then we could actually be able to increase either the voltage or the current output from the devices. So if we connect them in series, then we ended up getting actually the current that is the current that is this one, and the voltage is added up if we connected in series. And if you are connecting in parallel, then the current is added up and then the voltage is around 0.5 volts. So we could then light up actually a small LED that is using this. So using the moisture, we could light up this small LED. So this particular device doesn't really have any external source apart from the moisture. So we are only giving the energy from the moisture, and then we are converting into electrical energy. So these in principle can be used for moisture for some humidity sensing applications. So the same, can we do this so right now this system actually, the previous system that I had shown contains lead. Can we do it also for the lead free systems? So we tested that theory, because in the case of the previous one, we have lead iodide plus the methylammonium iodide, where we have the methylammonium iodide which is forming the ions. So can we do the same thing for the tin based system? So we checked the same thing for the tin based system by using different concentrations of the methylammonium bromide and the tin bromide. And you see that with the 4:1 ratio, we have the maximum current density and the maximum voltages that we could obtain for these devices as well. So in principle, we could get actually the moisture to electricity conversion not only with the lead perovskites, but also with any perovskite, because here the tin bromide or the SnBr4 is only acting as a scaffold for the ions to be held. So that's the reason why we could still see the generation of this electricity from these devices. So the mechanism is something that we propose like this, where we have, when the humidity is higher, we have the ions that are generated, and these ions are formed at the grain boundaries, because of which we have a formation of a double layer, and the voltage is generated because of this double layer, and the current is coming up because of the movement of these ions that are generated. Yeah, if we connect them in series, then we could increase the voltage and the current, and this is the connection where we can see that when we connect them in parallel, where the current is added up. When we connected them in series, then the voltage is added up in that case. So we could use this for some niche applications, like charging up some small devices like a capacitor or some tablets and so on. And with that, I would like to conclude my presentation, where we saw that if we allow it with bismuth, then we ended up getting actually the white light emission, where the emission is completely covering the entire visible part of the spectrum. So this is actually a single component white light emitter, which means that we don't need to use a RGB combination to get the white light emission, but we can use a single component to get a white light emission. And I have also shown this with the dimensionality, with the humidity, we have the dimensionality tuning of the perovskite, which can be used for the self-powered humidity sensing, or for any kind of small niche applications to charge for charging those devices. With that, I would like to thank actually the group members, without whom this work would not have been possible. And the students marked with the blue are the ones who actually contributed for all the work that I have shown today. And also I would like to thank the collaborators in the department and also outside the department, and from Monash and also from NTU. And also the funding agencies. So these are the funding agencies, and also for the IITB seed grant. And we had actually some support from the IRCC to purchase the glove box. So for that also we would like to thank the IRCC. Thank you all for your attention.